everybody. I hope that you're having a good holiday weekend, and we barely started the semester, but there's a lot of stuff to learn, and we're going to have more holidays as we head towards November. So I thought it would be good to get a head start and try and learn some of this material early. And so I'm making this video for you so that you can start to think about Bernoulli and homogeneous differential equations and start working on homework so that you can kind of get ahead of the game a little bit. Unfortunately, I'm a very, very long way from a classroom, so I'm going to have to do this in a very traditional way on pencil and paper. And I'm going to try and get my camera to take a pretty good video of this for you so you can kind of follow along. And of course you can always pause and rewind and watch things again if you need to. But anyway, I just wanted to let you know that I don't have a whiteboard, but I do have paper, and I am just going to do a very traditional explanation of section 1.8 of our book. Now, up to this point, we've learned how to solve separable and linear differential equations. So I hope by now that you've had a chance to practice that a little bit. Separable and linear differential equations are two of the most fundamental of all differential equations that you ever have to solve. Well, the question is, what do you do when you have a differential equation that's not separable or not linear? It turns out one of the clever tricks that you can use is you can take your differential equation and perhaps there will be a way to convert it into a new differential equation that is separable or linear. That's the strategy that I'm going to talk about in this video. It's called change of variables. Sometimes you can take a differential equation that's not separable and not linear and use a change of variables in order to make it either separable or linear. Okay, so this is one of the tricks that people like to use. They take an unfamiliar problem, one that they don't know how to solve, and convert it into one that they do know how to solve by using a change of variables. Okay, I'm going to show you how that works. But as always, I promise that I'm always going to give you a recap of what we learned in the previous lecture before we move on to the current lecture. So I'm going to see if you guys can see this. Right here on this paper is a recap of the lecture from before the break. We were talking about first order linear differential equations. There's really three steps that you have to use when you're trying to solve a first order linear differential equation. First thing you have to do, as you can see in my notes here, is step one is you have to find an integrating factor. Okay, so remember that the form of a first order linear differential equation is what I've got in the box right there. Y prime plus p of x times y equals q of x. Okay, so the p of x is very important. That's the part that's multiplied by y. So the integrating factor for this linear differential equation is given by the formula that I've got right here. It's just I equals e to the integral of p of x dx. Okay, so you have to calculate that. When you're doing the integration, you don't need to add a plus c on that because in this case, you're just looking for one integrating factor that works. Okay. If you take the original differential equation up here and you multiply it through by the integrating factor, the left-hand side is going to turn into just the product rule derivative of the integrating factor times y. Okay? So the derivative of that product. On the right-hand side, you will have multiplied through by the integrating factor, so you'll now have the original q of x times I. All right? Once you've written that down, it's very easy to solve for y. You simply have to integrate on both sides and then divide by I in order to get y by itself. That's the method for solving a linear first order differential equation. Okay? What I want to talk about next are two more types of differential equations. Okay? So in section 1.8 of our book, we're going to talk about change of variables. So what I was talking about a few minutes ago. And there are two specific examples of this. There are, of course, many examples of where you could use a change of variables to solve a differential equation. I'm only going to show you two specific examples just to get the idea of it. The first one is I'm going to talk about Bernoulli differential equations, and then I'm going to talk about homogeneous differential equations. Okay, and it turns out that each of these differential equations can be solved by using a change of variables. In the case of a Bernoulli differential equation, if you apply a change of variables to it, which I'm going to explain in a few minutes, you'll always end up with a new differential equation that's linear, and you solve that one instead. Okay? On the other hand, if you start with a homogeneous differential equation and you apply the change of variables that I'm going to explain in just a minute, you end up with a separable differential equation. All right? Now we know how to solve linear and separable differential equations already. So what we can do is, to solve a Bernoulli or a homogeneous differential equation, we can apply the change of variables that's indicated by this arrow and then replace our original problem with a new problem that we already know how to solve. Okay, I hope that the overview kind of makes sense. Let's start getting into the specifics of this now. Okay, I'm going to try and move this camera over here, see if this works a little bit better for me. So I'm going to start with the definition of a Bernoulli differential equation. Okay, a Bernoulli differential equation, okay, has the form. So this is the very important key, is to look at what is the form of a Bernoulli differential equation. A Bernoulli differential equation has the form, so let's write it down, y prime plus p of x times y equals, now so far that looks the same as the left-hand side of the linear differential equation. But here the difference is going to be that on the right-hand side we have q of x times y to the n power. Okay, so that power of y, right? Remember that for a linear differential equation, you cannot have that. You cannot have powers of y like that. Okay, so this is not linear, but it's kind of close to linear. So what we're going to do is we're going to do a change of variables and make it linear. So this is going to be something very important for you guys to know. Here is how you do the change of variables. Okay, so the change of variables, I'm going to use a u for this. Okay, and the formula is u equals y to the 1 minus n. Okay, now I have another video which is already available on the class webpage in this particular section 1.8 that sort of explains why that particular change of variables, notice that the 1 minus n is the exponent here, the n is the same n that you have right here in the form of the Bernoulli differential equation. I have a video that's going to explain why this change of variables converts this differential equation into a linear one. I'm not going to go through that right here on this video. I'm simply going to tell you what you're going to get if you take every single place that you see a y and turn it into terms of u. Okay, that's what a change of variables does. We get rid of all of the y's that we see in this equation and come up with a new equation that only has u in it. Here's what you're going to get. You will get, okay, just going to say it that way, u prime plus 1 minus n times whatever the original p of x was times u equals 1 minus n times q of x. This is another equation that you sort of want to have memorized. There's not a lot of formulas in this class, but here in this screen you see 3 of them that are all really pretty important. The form of a Bernoulli equation, okay? the change of variables that you need to use to convert a Bernoulli equation, and then here's what it converts into right down here. And notice that this is linear, right? Here is sort of your new p of x, and this whole thing over here becomes your new q of x. Otherwise, it's the same exact form. Notice that the y to the n is now gone down here. We do not have u to the n or u to any power whatsoever, right? That's why this equation here is actually a lot nicer than the original Bernoulli equation. This one we can solve very easily by simply using the procedure for solving a linear differential equation that we just reviewed a few minutes ago. Okay, let me try an example with you, okay? So I'm going to do an example right here. Okay, let's suppose that I wanted to solve the following problem. Let me start on a new page so that I have plenty of room to show this to you. So let's solve, sorry, a little unsteady with my camera right here. Solve y prime plus 2x over 1 plus x squared times y equals xy squared. Let's try this example right here. Okay? Notice that here is sort of the p of x that we're used to seeing, and this right here is the q of x that we are used to seeing, but we have y to a power right here. Remember that that power is what I usually call n. So n would be 2. So if you believe the notes that I gave you on the last page, what we need to do is we need to set u equal, right? I'm going to set u equal to y to the 1 minus n, which in this case is 1 minus 2, or in other words, y to the negative 1, which I can also think of as 1 over y. So u is going to simply be the reciprocal of y. Okay, let's just keep that on the side for right now. The key thing that I need to do is use the formula. I'm going to write it again one more time here. Use the formula for the new differential equation, okay, here it is, that you get after you apply that change of variables. So remember, n is equal to 2 right now in our example. So this is going to become u prime. 1 minus 2 is just a negative, and then we have the p of x that was given in the original problem. That's times u equals, and then again we have a negative 1 for the 1 minus n, and then the q of x, which is just x. Okay? So there is the new differential equation, and this one is, as promised, linear. Okay? This is a linear differential equation. Okay? Let's just practice solving it. Remember, we have to find remember there's 3 steps. The first one is we have to find the integrating factor, e to the integral of p of x dx. And please remember that the p of x now is this whole thing, including that minus sign. So I have a minus sign on the p of x, which I don't want to forget. And then I have the integral of 2x divided by 1 plus x squared dx. That can be done with a simple substitution, right? So this is e to the negative. What you're integrating here is really just du over u. So you're just going to get the ln of u, and I don't need absolute value bars on that because 1 plus x squared is already going to be positive, okay? But I am going to take that minus 1 and put it up as an exponent, and then I'm going to cancel the e and the ln. So I am going to get the following expression, 1 over 1 plus x squared. That's the integrating factor. Okay, step 2, I take the integrating factor, 1 over 1 plus x squared, I multiply it by my unknown function, which at this moment is u, and the product rule derivative of that should equal my integrating factor times the q of x that I had, which is right here. Here's q of x for this problem, so we have negative x right there. Okay. Hopefully so far so good. Finally, I just have to integrate both sides. So I'm on the left, of course, I'm just going to get rid of the derivative that I see there. And on the right, when I do this integration, I'm going to take out the minus sign from right here. And then I need to put in a 2. So I'm going to pay the price by putting a 1/2 in there. And then the rest of it is, again, just the integral of du over u. The antiderivative of that is just 1 plus x. The ln of 1 plus x squared, okay, and then plus c. So I'm kind of skipping some of the steps of the integration, okay, just because I know you guys can do that. Okay, we can then solve this for u by just multiplying through by 1 plus x squared. Sorry for all the shaking around here. Okay, so it's going to look like this. Now, that is not my final answer for u. Well, it is my final answer for u, but that's not the final answer to the problem, because remember, I'm really trying to figure out what y is. So what I'm going to do is take the reciprocal of u to get y. So let's come back down here. I'm simply going to get y by taking 1 over everything that I just wrote down. Okay? And so that's how you solve a Bernoulli differential equation. Okay? You simply convert it to a linear differential equation by using the change of variables that I had given to you before. Notice that the change of variables, which is right here, we didn't use that until the very, very end, down at the bottom of the problem, when I was going from what u was equal to what y was equal to. So you kind of just keep the change of variables, u equals 1 over y, in your back pocket until you're ready to actually take advantage of it. Okay, so that's an example of a Bernoulli differential equation. I'm going to go to a new page here, and I want to show you one other example of how changes of variables can be used, and it's called homogeneous differential equations. Okay? So a homogeneous differential equation, this is just to give you another example of how to use a change of variables on a different kind of differential equation. I first want to explain what I mean by a homogeneous differential equation. So I'm just going to point it out this way. A first order differential equation is homogeneous. A first order differential equation is homogeneous of degree 0. I don't always say all of those words. I'll just say homogeneous sometimes. If it has the form y prime. So in other words, if you get the y prime by itself, then there's some function of x and y on the right hand side, but there's a specific requirement here that I want to emphasize, which is that the function f has to have the following property. The function f has to be homogeneous of degree 0, which what that means is the following. Let me write it down here. F of xy is equal to f of xt and yt. What this really means is that as you're inputting the x and the y into the function that's occupying the right-hand side of the differential equation, imagine putting a t next to every single x and every single y that you see in the expression on the right-hand side. If you do that and you put xt everywhere you used to have just x, and you put yt everywhere you used to have just y, and if they're the same, meaning that the t's essentially just cancel out from the differential equation, then we call the differential equation homogeneous of degree 0. So this is what we're talking about. So let me just give you a quick example. If you had f of x and y equal to x over 2x minus 3y, okay, then if you took that and everywhere you see an x, you now put xt instead, okay, and everywhere you see a y, you put yt instead. So every x has been changed to xt. Every single y has been changed to yt. What you should notice is that on the top and on the bottom, you can actually just factor the t's out and cancel them. And what you're left with is the original f of x and y that you had in the first place. Okay, so that's homogeneous of degree 0. Okay, that is homogeneous of degree 0. Now, on the other hand, if we had something like this, where we had, let's say, x over 2y squared minus 5x, okay, if you try to put a t next to every single x and next to every single y, notice that you'll actually get 2 t's right here. And if you try to get all of the t's to disappear, you won't be able to do it because there's t squared right here and there's just t right here. And so you can factor one of the t's out of everything, but you'll be left with an extra t right here. This is not homogeneous. This is not homogeneous. When you're thinking about what this term homogeneous really means, what we're really saying, guys, is that there has to be a balance of x's and y's. They have to have the same weight in every single term. So just as one more example, the t is really measuring the weight of the expression of the x's and y's. So if I had something like this, okay, just to give you one more example of it, okay, if you had a function like that, look at the weight of every single one of those terms. There's 3 x's here, there's 1 x and 2 y's here, and there's 3 y's here. On the bottom, 2 x's and 1 y, and 3 y's. If you put t's next to every single x and every single y that you see everywhere in the circled parts that I've drawn here, you're going to have 3 t's here, 3 t's here, 3 t's here, 3 t's here, and 3 t's here. And you'll be able to factor and cancel those t's, right? This one is homogeneous. Okay? I hope that this is making sense. It's important that you understand what a homogeneous differential equation looks like so that you'll be able to solve these problems. Now, let me tell you how you actually solve a differential equation that's homogeneous. Suppose that you have a differential equation that you've written like that, and suppose that the right-hand side is homogeneous so that that little t trick works, okay? Then the question becomes, well, how do you solve the differential equation? Well, again, we're going to use a change of variables. That's the title of section 1.8. Okay, that's what we're talking about in this video. Now, in the Bernoulli differential equations, we had one change of variables, which was, you'll remember, was u equals y to the 1 minus n. We're not going to use that here. This is going to require a different change of variables, and the one that we're going to use is, the way I like to write it is like this: y equals xv. So we're going to take out all of the y's and rewrite them only using x and v. Okay? Now, of course, that also means that we're going to have to take out y prime. Let me just tell you, it's often useful, I think, to just write down what y prime is right off the bat. So what y prime is going to be here is, if I just use the product rule on this, the first term times the derivative of the second plus the second term times the derivative of the first, there's y prime. And you can literally put that expression in on the left side of the homogeneous differential equation. What you have to trust me on is that when you use this change of variables and plug everything into the other side of the differential equation, you'll be able to get rid of all of the y's. Well, that's kind of clear. You're going to take every single y that you see and change it to x times v. What you're going to end up with is a new differential equation. So what you're going to get is a new differential equation that is, that in this case, these differential equations always become separable. They always become separable. Okay, so here's an example. Let's just do a quick example of this. Suppose I ask you to solve y prime equals y over x plus the square root of 16x squared minus y squared all over x. Okay, let's suppose that's the problem that we want to solve. Notice that this is the right-hand side. This is my f of x and y. And if you look at that and you imagine putting a t next to every single y and every single x. So here, if you put a t here and a t here, they're going to cancel, right? If you put a t right here, now that's going to cancel, but it takes a minute to see why. If you put two t's next to the x squared and the y squared and then factor that t squared out of the radical, it becomes t again, and then you can cancel it with the denominator. So you have to do just a little bit of inspection, but the point is this is homogeneous. Okay, so I'm going to take y prime and replace it with x v prime plus v. Okay, I'm going to take y over x. Now that y is xv, I'm going to divide by x. And then inside the radical I have 16x squared minus x squared v squared all over x. Okay? Notice that this is just v right here, and so it's going to cancel with the v right there. Okay? And what else we have is on the right-hand side, I can take the x squared, factor it out of the radical, and cancel it with the x that's on the bottom. It leaves me with just the square root of 16 minus v squared. As I said, this always becomes separable. To see how to separate it, I like to rewrite my v prime as dv over dx. And then I'm going to move all of the v stuff to the left side and all of the other stuff to the right side. And then I'm going to integrate both sides of that. When you integrate on the left side, you're going to maybe want to use a table of integrals. It turns into the arc sine of v over 4. On the right-hand side, it's the ln of absolute x, and we put our plus c there. Okay? Now we just have to figure out what y is. I'm going to multiply, first I'm going to take the sine of both sides to cancel the arc sine that I have there. So I'll have the sine of the ln of the absolute value of x plus c. Okay. And then I'm going to multiply through by 4. I need just a little bit more room. I'm going to multiply through by 4. I'm going to get v equals 4 times the sine of the ln of absolute x plus c. And of course v is really just y over x if you remember the change of variables. So y is just x times v. So it's just x times what we just wrote down. Okay, so this is just a quick example to show you how to solve a homogeneous differential equation by using that change of variables right there. Okay, so I've shown you Bernoulli and homogeneous differential equations. I hope that it's made some sense to you guys. I appreciate you paying attention and listening to my video tonight, and I'll be back soon to answer questions about that. Shoot me an email if you want to. I'll be glad to help you out, and I'll see you guys again soon. Thanks a lot for watching.